Okay, so before we're uh, before we're done with this semester, we've got one more differential equation that we'd like to solve, and it's a differential equation that describes an adiabatic process. Adiabatic process means the heat transfer is zero. Adiabatic process means Q is zero, which means that the change in internal energy is equal to the negative of the work done. And let's talk about calculus. Some small change in the internal energy is the negative of some small amount of work done. Just an infinitesimal change in the temperature, an infinitesimal work done. Since it's an infinitesimal work done, it is the pressure that exists times the infinitesimal change in the volume in this particular instant. The change in the internal energy of the ideal gas has to do with the it's the internal energy. We've got 3/2 NKB dt. Now, based on what we said in our previous segment, 3/2 N, capital N, K sub B, we said was equal to NR dt. But 3/2 R, that's the molar heat capacity at constant volume for a monatomic ideal gas. And molar heat capacity dt equals negative P dV. Now we've got, let's assume that the number of moles of the gas is constant. We're not going to let any out. But we do have three variables that are interrelated by the ideal gas law. We've got the temperature, the pressure, and the volume. The left-hand side of this equation would integrate dt. The right-hand side would integrate dV, but P is a function of both of those. So let's use the ideal gas law to express the right-hand side. Let's see, PV equals nRT. So we can cancel, like P would be nRT over V dV. Right? Okay. So we've got the number of moles on both sides. We can cancel that. Let's see here. Let's divide both sides. Let's get the T's on one side and the V's on the other side. So we've got dt over T. Actually, you know what? Let's bring everything to one side and see if we can get some cool stuff happening there. So we've got, and just for, let's keep CV as 3/2 R, just for fun. So we divided both sides by T, and okay, cool. Let's bring that plus R dV over V equaling 0 because we brought that term to the other side. Now, 3/2 R and R what if we divide both sides by R? Yeah, I mean, we can cancel the R. Three halves, though. I want to handle that. This is for, let's see. Gamma for a monatomic ideal gas is the ratio of Cp to Cv, which for monatomic would be 5 halves over 3 halves R. So that's 5 halves. If we subtract 1, then that gets us, so gamma is 5 over 2. But if we subtract 1 from both sides, well, yeah, okay. Gamma minus 1 is 3 over 2. So this 3 over 2, that's gamma minus 1. Okay, that's pretty cool. Where do we go from here? Actually, you know what? I think I've made an assumption here that this is, in fact, a monatomic gas that I don't need to make. Or at least I shouldn't have to make it, right? An adiabatic process is an adiabatic process. So I think I've got to go back to the drawing board. Hold on. Let's let's see. Let's just write this as NCV delta T. I had that before, and let's just stay with it. The N's we canceled. Let's collect the T's and get dt over T. Let's divide both sides by CV so that on this side we have negative R over CV d capital V over V. And then we got to figure out this this ratio here, R divided by C sub V. It's tempting to just replace this with 3 halves R and then cancel, and we end up with 2/3. But we want this to be general for any working substance. It could be diatomic. I don't know. So instead of doing that, let's think about the fact that the difference between C sub P and C sub V is R, which means we could replace this R with that difference. So this ratio here is the difference between the molar heat capacities divided by the molar heat capacity constant volume. And that it looks like C sub P over C sub V minus 1. But C sub P over C sub V, that's gamma. So R over C sub V, there's the gamma minus 1, and it's one that doesn't care whether it's monatomic or diatomic, and I did something funny before. This is how it should look. Let's bring everything to the same side again so that we don't have this minus sign rattling around. dt over T plus gamma minus 1 dV over V equals 0. And now this belongs to something else. From here, Let's integrate term by term. This term will get us the natural log of t. This term will get us the natural log of v, and we'll go from there. So let me start here. T over t plus gamma minus 1 dv over v equals 0. Integrate here, it gets us natural log of t. Gamma minus 1 is a constant. Integrate here, that gets us natural log of v. Integrate the right-hand side. What's the integral of 0? 0 plus integration constant. This is an indefinite integral. We didn't declare endpoints. So the indefinite integral, somewhere along here, there's a constant. We can collect all the integration constants over here. There's some number over here. I don't care what it is. The rules for logs allow us to combine the natural log of t. This coefficient of a log is the log of the thing raised to the power gamma minus 1. And the sum of two logs is the log of the product, t v to the gamma minus 1 equals, again, some constant. Let's exponentiate both sides. E to the that cancels the natural log. The product of t and volume raised to the gamma minus 1 is, again, constant. E to the something is just another number. I don't care what it is. It's some constant. So during an adiabatic process from temperature 1, volume 1 to some temperature 2, volume 2, this product needs to be constant. So if we evaluate it at state 1, then we have to evaluate it at state 2 and get the same answer. That's not an 8, it's a gamma. Okay, cool. Now, from the ideal gas law, we could write this in terms of temperature, or I'm sorry, in terms of pressure if we wanted to. If we solve for T, we've got P V over N R equals T. So this T1 gets us P1 V1 over NR, and this T2 gets us P2 V2 over NR. The NRs cancel, and V1 times V1 to the gamma minus 1, we add the exponents. This is raised to the 1, so we end up with just gamma. P1 V1 to the gamma, P2 V2 to the gamma. Cool. Okay, so this is ways to leverage the ideal gas law to talk about the relationships between pressure, volume, and temperature in an adiabatic process. There's one last thing to talk about, and that's to ask how much work is done, which makes me think that we've got to re-solve that differential equation that we wrote at the beginning with, du equals negative dw. But let's cheat a little bit. One differential equation is enough for this particular segment. It's still true that macroscopically speaking, not infinitesimal, that if the internal energy changes, it's the negative of the work done. But okay, so that means the work done is the negative of the internal energy change, which we know is negative NCV delta T for an ideal gas. But the temperature change, NCV CV T2 minus T1, always final minus initial, but T2 how did it go? T is PV over NR. So this is negative N CV T2 P2 V2 over NR minus P1 V1 over NR equals, the ends cancel. CV over R is the reciprocal of R divided by CV, which is what we said was equal before to gamma minus 1. So CV over R is 1 over gamma minus 1. Negative 1 over gamma minus 1 from P2 V2 minus P1 V1. If you wanted to, you could absorb the minus sign and switch the order of the subtraction. But that's fine. You could absorb the order. You could make it 1 minus gamma here too. But that's the work done during an adiabatic process. I think we could also find it by expressing the pressure as a function of the volume that we, according to what we just wrote, with the raised to the gammas, and integrating directly, right? The integral of pressure as a function of volume, d volume, and figuring out what that expression is. It should give us this. Okay, so now that we know the behavior during an adiabatic process, we've got from one point to another point, and then there, and then back, and then up. And if we look back at the slide, kind of looks like a banana, actually. If we look back to the slide, A, B, okay. Point A, point B, point C, point D. The transition from A to B is an isothermal process. Okay. How good is this? That's the question, right? This Carnot engine. How good is this Carnot engine? Let's define efficiency E as the ratio, right? The return on our investment. If we invested QH, how much are we getting back? How much W are we getting for our investment? So we need to figure out what is the net work, the net useful work in this cycle, and how much heat did we invest? This is the game. Okay. Remember, we also know that we invest QH, we want some work done out of that, and then whatever's left over, the part that we don't get to use, that's the QC. So W here is QH minus QC over QH, so it's 1 minus QC over QH, so that's a useful result. Okay. But that still doesn't tell us what the deal is with the temperatures here. Okay, so let's start making stuff up. The transfer from A to B is isothermal, which means in the work done in an isothermal process, I think we know is a natural log. right? Integrate pressure dV. If it's isothermal, then okay. So let's say the temperature is constant. Pressure is nRT over V dV, and we need to integrate that. nRT is constant. We could pull that out, and we're talking about the natural log, yeah, of V from V1 to V2. Okay, great. So the work done here, we know is, but that's also because in an isothermal process, delta U is 0, which means Q and W are equal. So if this is the work done, it's also QH. So here we know QH is nRT T hot, I guess, the temperature at which our initial investment is made. We know that it's all one temperature because it's isothermal. ln of V2 over V1. Okay, then we get adiabatic expansion. Then we get an isothermal compression. All right. All right, hold on. Not 2 and 1, but B and A. And this is the trick. The isothermal compression that would get us QC so that we could finish the calculation of efficiency. We need to know what that third volume is, the volume at point C, and it depends on the fact that this process B to C is adiabatic. So, I gotta erase this for a second. For an adiabatic process, Q is 0 and delta U is related to the work done. T V gamma to the minus 1. T1 V1 equals T2 V2 to the gamma minus 1. That's from that stuff we just had. Now, okay, so we're talking about the temperature at point B, which is the temperature of that whole first process. So this is the hot temperature. V1 is the volume at point B. T2 is the temperature of the cold reservoir, the temperature of the exhaust, the temperature at which the isothermal compression is about to happen when we exhaust our leftovers QC. This volume here, so this H is hot. This C is, I'm gonna write what? I don't know what I'm gonna write. T cold, just do it that way. This volume is the volume that we have at point C. Okay. So VB, let's solve for VB. Huh? Well, okay. And then, oh man, what do we do next? All right, so let's talk about QC, which would be the work, the heat that is transferred out of the system during isothermal compression, C to D. equals nRT cold at the temperature at which that happens, ln of now V2 to V1, VD to VC. VD is less than VC, so this is going to be a fraction that is smaller than 1. The natural log of that is going to be negative, which is good because QC is supposed to be heat transferred out of the system, which we said was negative. Okay. I guess we should finish the story just to be safe. The adiabatic compression from D to A gets us a relationship very much like this one. Just in case we need it. I'll put it over here. TC, the temperature that we have, oh gosh, all right. T cold, the temperature that we have at point D, because we just did this isothermal thing here. The volume at point D raised to the gamma minus 1 equals TH, the volume at point A raised to the gamma minus 1. All right, so now we just have to put this all together. Let's see what that'll look like. The efficiency equation asks for the ratio of QC to QH. The efficiency is 1 minus QC to QH. All right, let's find the ratio. We'll come back to that. Let me just write QC minus, or QC over QH for now. QC over QH equals, QC is this thing. nRT cold, natural log of the ratio VD to VC over nRTH, natural log of the ratio VB to VA. All right. The N's, the R's, they cancel. And this is T cold over T hot. And this is the ratio of natural logs. Oof. Okay. Natural log of VD over VC over natural log of VB over A. All right. What happens now? So far, we've used 1 and 2 of our 4 equations, so I guess we got to use these other ones. The natural logs that we're talking about is the ratio between D and C, and the other ratio is from A to B. All right, so hold on, let's rearrange this. I think we're set with this one. I'm going to erase that. And I'm just going to copy this one up here, but I'm going to reverse the order in which I write them. So it's TH VA gamma minus 1, because we're talking about B to A. And then this one is T cold. Oh, neat. TH T cold. That's fun. T cold VD to the gamma minus 1. And that's, all right. What if we take this equation and divide it by this one? That would get us the ratio of VB to VA, but it would get us the, oh shit, that would be upside down. Unless we, introduce a minus sign here, we can change the order of the division. And then VCVD. Think about the log rules, right? The log of a quotient is the difference of the two logs. If we factor a minus 1, it changes the order of the difference, which it makes the reciprocal of the quotient argument. That means, okay, so now wait, let's divide TH over TH. We've got VB over VA to the gamma minus 1, and VC gamma minus 1 over VD to the gamma minus 1. Oops, that's not a subscript. Well, we could take the gamma minus 1th root of this equation. We end up saying that the ratio from B to A is the same as the ratio from C to D, which means the natural log of that ratio divided by the natural log of a ratio that is equal to that ratio. This is just 1, which is pretty cool. This ends up reducing to negative T cold over T hot, which is really nice, and it lets us write the efficiency equation for a Carnot engine, this kind of process, as 1 minus T cold over T hot. Your job in this week's recitation is to show me that between two temperatures, this is the best one we can get. Otto and diesel are less than that. And you'll follow a method very much like this to get from point A to point B to C to D and back. All right. So what's the story here? It's not perfect. The efficiency isn't 1 unless this term is 0. And there's only 2 ways I can think of to get a quotient equal to 0. Well, even to look like 0. Well, the first way is to make the numerator 0. So the cold temperature is 0. And since this is all ideal gas law, we're talking about Kelvin. This has got to be 0 Kelvin. So we need an engine that operates at 0 Kelvin, and that has problems that I'll come back to in a second. The other way we can get this to look like 0 is if we make T hot infinitely large, right? And then it looks like some number divided by infinity, which looks like 0. But the trouble with that is that, if we make T hot infinite, or arbitrarily large, then a whole bunch of other things happen. The pressure goes arbitrarily large as well because they're directly proportional. And so either we explode the engine with the internal pressure, or we melt the engine with the internal temperature. And we can make engines that are only so strong given the materials available to us. We can make engines that are only able to withstand certain temperatures given the materials available to us. So we can't make this arbitrarily large. We can make it pretty large, several tens of thousands of Kelvin, but it's still not zero. And the only way to get an efficiency of 100%, is if T cold is 0. Now, imagine, by the way, I'm going to skip the sections in chapter 20 that are about refrigerators. Suffice to say, they are the backwards of engines. We input some amount of work and we transfer some amount of heat out of a cold reservoir into a hot reservoir. Take some thermal energy from inside the refrigerator and pump it outside where the temperature is greater. If we weren't doing work, the heat would flow the other way, like from the metal box into the ice and melt it. So the work that we put in gets us the ability to coerce the thermal energy to move the other way. So we can, and that's as much as I'll say about refrigerators, we can lower the temperature of one part of a system by moving thermal energy to a different part of the system at a higher temperature by doing work. But here's the thing. How do we get a system to have a temperature of absolute 0 Kelvin? The way that I cool things down, like if I wanted to cool down this seltzer water, I would put ice in it. I would find a thing at a lower temperature and put that in this thing, and they would reach a thermal equilibrium somewhere, somewhere greater than whatever the low temperature was. And that's problem number one. I've got to find a thing at a lower temperature to cool a system down. So we've got a thermal system, and we can put cold things in, cold things in. We can find very, very, very cold things like liquid helium. We can get to 4 Kelvin. We can get, if we really, really try, we can find a thing that maybe is 1 Kelvin. But how do we get colder than that? It's hard enough to find a thing that is a temperature of 1 Kelvin. If we add that to some other system, if we've got a system at 1 Kelvin and a system at 2 Kelvin, if we combine them, it's a system at 1.5 Kelvin. It'll never be a system at 1 Kelvin unless we're adding an infinite amount of this 1 Kelvin stuff to make sure that the temperature at which we reach thermal equilibrium is 1. And that's the problem there. So the only way to get a thermal system to a lower temperature than that is to run a refrigerator, to do work. But the more work we do to move the heat, the thermal energy, the internal energy out of this system, to get this system closer to 0, the harder it gets. It's like a vacuum, right? The more you try to create a vacuum, the harder it gets, because nature wants to fill it. And the same thing is true here. If we have a system that we're trying to get very, 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 very cold, as it gets colder and colder and colder and colder, it lives in an environment that is warmer than it. So there is some thermal gradient between the system and its environment. And we can do very cool things with insulation to try to keep this, system isolated. But as we get closer and closer and closer to 0 Kelvin, any amount of heat current is enough to keep us from reaching 0 Kelvin. So we need an infinite amount of insulation to make sure that no heat current reaches this system, that it is entirely isolated. An infinite amount of insulation, okay, so that's not real. Or that's the problem. Or, okay, so wait, what if the surrounding environment is also at 0 Kelvin? Then that environment and our system would be at in thermal equilibrium. They'd be at the same temperature, and no heat, no transfer of thermal energy would need to occur. But that means we needed to get this system to 0 Kelvin in the first place. To get the environment to 0 Kelvin. And you can see where I'm going with this, I think, by now, that there is it is impossible to cause a system to have a temperature of absolute zero by completing a finite amount of thermal processes. We either need to put in infinite work, step thermal processes infinitely forever, doing infinite work, or we need infinite insulation, or we need all of the possible environment for a system to already be at absolute zero, which means we can't use anything anyway. In some resources, if you look this up, it is referred to as the third law of thermodynamics, that it is no system can reach absolute zero in a finite number of thermal processes. And it's just a problem with asymptotes, which means the numerator will never be zero, which means the efficiency of a Carnot engine will never be 100%. Ever. It's strictly speaking, there doesn't really need to be a third law of thermodynamics, and it's been talked about, but it's all part of the second law of thermodynamics, and that is that it is not possible for a 100% efficient thermal engine to exist, because the numerator can't be zero, because we can't reach absolute zero in any finite number of steps. There's no way to engineer a place to exhaust to that has a temperature of 0 Kelvin, which means we can't do it. We cannot make a perfect engine. And that is a big deal. The second law of thermodynamics says that it is not possible to convert a heat transfer entirely into work without any losses. There must be some QC. It is not possible to reach absolute zero. 0 Kelvin, not possible to reach 0 Kelvin. Can't be done. That's not okay. That's 0 Kelvin. Not possible to reach 0 Kelvin. 100% efficiency. Can't be done. It's not possible. The second law of thermodynamics is a statement about what is not possible. Every other law that we've encountered in the entire semester has been a statement of what must be true, what must be constant. You know, we've got conservation of energy, conservation of momentum, conservation of this, conservation of mass, conservation of this. The second law, even the first law of thermodynamics, is conservation of energy. The second law of thermodynamics is fundamentally a different kind of law. It's a law that talks about what must be unequal, what must be unconserved. It has to be true that there are some losses. The work done by this engine cannot be equal to the heat transferred in of our investment. There must be some loss to this thermal system. That we are required to have non-conservation, in a sense, that there is only so much use we can get out of a thermal system, and this is a really, really powerful idea. I'll stop this segment there, and I think we've got one more to talk about.